Hello students, welcome back to physics sessions. I hope you all are performing the exams very well. Today we are going to discuss the waves chapter, IPE questions. That too, as per the weightage of the chapter, long answer questions are very important in this chapter. So myself, Sandhya, I will be helping you your inter IPE exams concepts from the chapter waves, long answer questions. Students, after your exams finished, that you're going to attempt the MSET, JEE or NEET. So for that information, you can download our app Spark Academy. Admissions are open for classroom and online coaching. There are short-term crash course and regular batches. Students, you can join us for live regular updates. For regular updates, in a week on Tuesday and Friday, we will be having the physics sessions. So you can contact for admissions any of these number which is displayed below, 913380172897752546 for JEE, MSET or NEET admissions. Students, let us go to the session plan. Today we are going to discuss the waves chapter, long answer type questions. Here the first question we are given with in this chapter mainly from the waves, stationary waves or standing waves. That concept is very important. So from the stationary waves, which types of questions can be asked as a long answer? So let us see here. Here we are given with explain the formation of stationary waves in stretched strings. So when the string is under stretching position, we can see the string appears like a loop. Means there are new set of waves are formed. Those waves are called stationary waves. You can see here, when the stretched string is plucked at the middle, transverse waves are generated. These transverse waves get reflected at its ends. These reflected waves travel in opposite directions along the length of the string. They combine together to form the stationary waves with nodes at the ends. You can observe at the diagram. See here, when the string is plucked. So when it is plucked at the ends, in the middle, you can see that formation of the transverse waves. So as it is propagating in a positive x direction, and at the other end also, it is plucked at the other end. So that wave reflects. So these new set of waves are called, the combination of these reflected waves which appears them moving in opposite direction along the length of the string, they form the stationary waves. And you can see at the ends of each loop, now the string, that plucked string appears like a loop. At each end of the loop, it is observed that N is placed. N means nodes. Means at the minimum amplitude. At the minimum amplitude, nodes are formed. N means nodes. At a maximum amplitude means the displacement is maximum. Either side of the loop you can observe. At a maximum amplitude, antinodes are formed. AN means antinodes. So at antinodes, amplitude is maximum. At nodes, amplitude is minimum. So let us see the mathematical explanation of a stationary wave. As a long answer, you need to discuss about the stationary wave and show it with the diagram how the nodes and antinodes are formed in the formation of the stationary waves. Means you just locate their positions in that formation. Next. So now we are taking mathematical analysis, which is the explanation about the stationary waves. So let two transverse progressive waves with displacements y1, y2, same amplitude, because when they reflect, moving opposite directions combined together, they can have the same amplitude. And same amplitude and wavelength are traveling in opposite directions. So now we are taking two such waves of their displacements. First one, y1, is equal to a sine kx minus omega t, means which is propagating in positive x direction. Next one, y2, so this one, positive x direction, it's a displacement. Next, this one, negative x direction is y2, its displacement y2 is equal to a sine kx plus omega t. It is propagating in negative x direction. So they combine together. So the principle of stationary waves is that combination of two reflected waves. Nothing but principle of superposition. So y1 plus y2 equal to a sine kx minus omega t plus a sine kx plus omega t. It is like sine a plus b plus sine a minus b form, which will be equal to 2 sine a cos b. So we have written this. A is common, so we have written a. Now sine a like sine a plus b, can take positive term first, next negative term. Sine a minus b will give you 2 sine a. Now it is a, it is b. It is a, it is b. It gives the result 2 sine a cos b. Can write it as 2a sine kx cos omega t. Now it is in the form of, compare with the general displacement of a simple harmonic progressive wave, it will be in the form of like a cos omega t. So AR means instead of 2a sine kx, there is a resultant amplitude of stationary wave. So now let us take that resultant amplitude. What we have seen in previous slide, y is equal to 2a, means small a given amplitude, 2a sine kx cos omega t. It can be written as AR cos omega t, where AR means resultant amplitude of stationary waves is equal to 2a sine kx. So after finding, it is the amplitude of stationary waves. AR means resultant amplitude. By the combination of two waves, resultant amplitude, which is of the stationary waves. So 2a sin kx, and we have known in that formation nodes and antinodes are formed, where amplitude is maximum, their nodes are formed, where amplitude is minimum, amplitude maximum antinodes, amplitude minimum nodes are formed. So it depends upon the kx value. It is the kx is nothing but like phase. So it depends upon kx value. So for what, at which positions nodes are formed, we see that. You can see when x is equal to 0, lambda by 2, 2 lambda by 2, 3 lambda by 2, amplitude becomes 0. Because in this formation, here x is equal to 0. You can observe at the diagram, here 0, and 0 to at this point, it is lambda by 2. Next, this node to this node, again lambda by 2. If we take antinode to antinode, the distance traveled by the wave is also lambda by 2. That way. If we are taking antinode to node, it will be lambda by 4. So you can say at 0, at lambda by 2, 2 lambda by 2, 3 lambda by 2, next is third node. 3 lambda by 2, 4 lambda by 2. So at those positions, amplitude becomes 0. These positions of 0 amplitude are known as nodes. Actually, we have a condition also, phase difference condition, that you need not to give in the question. You just tell what are the positions for the nodes. It depends upon the sin kx value. If this value is 0, amplitude 0, so nodes are formed. So at what positions it will be 0? 0, lambda by 2, 2 lambda by 2, 3 lambda by 2, etc. Next, when sin kx value equal to 1, then resultant amplitude will be equal to 2a. Sin kx equal to 1, this implies AR will be equal to 2a, which is the maximum amplitude. So when amplitude becomes maximum, that is 2a, positions of antinodes we can find. So at what positions amplitude will be maximum? Again you can see at the diagram. See. So node to antinode is lambda by 4. So from 0 to A means at lambda by 4 there is antinode. Next, 2 lambda by 4. Next, 3 lambda by 4. That way. So you can say lambda by 4, 3 lambda by 4, 5 lambda by 4, etc. Sorry, I mentioned 2 lambda by 4. Actually, that is 3 lambda by 4. Here, lambda by 4. And next, this position, 0 to here, 3 lambda by 4. Next, this position, 0 to this position, 5 lambda by 4, that way. So at these positions, antinodes are formed. And they're asking frequency of that transverse wave. Derive the expression for frequency of transverse wave. As a long answer, you need to give positions of nodes and antinodes in the formation of stationary waves. Next, frequency of transverse wave. First, how to calculate velocity of the transverse wave. That formula important. Velocity is equal to under root T by mu, where T is the tension applied to the string, because when the string is plucked at the ends, the combination of that reflected transverse waves mu set forms the stationary waves. So we need to take tension along the string, and mu is the mass per unit length or linear density of the string. This is the formula to calculate velocity of the transverse wave. But we need to find frequency. So we know that I'm writing here V is equal to F lambda. So from this, frequency will be equal to velocity by lambda. Keep in mind this formula. Next, they are saying distance between adjacent nodes is lambda by 2. Means if you take difference between any two successive nodes, we get lambda by 2. So that is the distance between two adjacent nodes. So that in string fixed at both ends, there must be the integrated number P of half wavelengths. So we get like that integrated number of half wavelengths, like segments like this, half wavelengths means one loop, two loops, three loops. So here node, here node, here also node, here also node. So between adjacent nodes, it is lambda by 2, which is nothing but half of the wavelength of the wave. So in the formation of stationary waves, when it is fixed at both ends, the string is fixed at both ends, we can see the integrated number P of half wavelengths. P means a segment or a loop. Next, here also lambda by 2. So integrated number of the half wavelengths, you can see. Now, so we can write that length of the string is, we are saying there are integrated number of the half wavelengths. So that integrated number is P, where P equal to 1, 2, 3, so on. So P of half wavelengths is being equal to total length of the string. So from that we can write lambda is equal to 2L by P. Yes. So wavelength of the wave is being equal to 2L by P, where P is 1, 2, 3, so on like that segments. But velocity is equal to frequency into lambda. Frequency we can represent with F or mu. This is mu lambda. So to find the frequency, F or mu will be equal to V by lambda. V we have known, since V is equal to root T by mu. So this is equation 1 actually. So equation 1, 2 and 3. We can write frequency of the stationary waves in a string is V by lambda. V is T by mu. 1 by lambda means P by 2L. So this is the formula to find the frequency of stationary waves. And that frequencies have particular names in that formation of stationary waves. So all possible frequencies are harmonics. So you can say if P is equal to 1, means only one segment is formed like this. So here length of the segment is lambda by 2, then lambda is equal to 2L. So that is called first harmonic. So mu1 is equal to 1 by 2L into lambda value, means P value you can substitute 1. You can use this equation, substitute P value 1 by 2L into under root T by mu. Next to P equal to 2. Then the second harmonic can be written as, actually it is 2 by 2L into under root T by mu putting P equal to 2. So it is 2 times of first harmonic. Next, put P is equal to 3, then the third harmonic will be observed, that is 3 times of initial frequency, that is the first harmonic. So the frequencies are in the ratio 1:2:3, so on. So this is the expression for frequency of stationary waves in a string, where P is number of loops or segments. So in the formation of stationary waves, it is observed that integrated number of half wavelengths are formed. So we have taken total length is equal to P into lambda by 2, where P is an integer. From that we have written lambda value. So that lambda value substituted in the frequency formula. So we have taken their harmonics ratio. So all that possible frequencies are called harmonics. So for the first loop, first harmonic, 2 loops, second harmonic, 3 loops, third harmonic. That way frequencies are in the ratio 1:2:3. So this is a long answer, important long answer, formation of stationary waves and expression for frequency of the stationary waves. Till their frequency ratio you need to write. Next, formation of stationary waves in an air column enclosed in open pipe. Derive the equations for the frequencies of the harmonics produced. So in open pipe, stationary waves, formation of stationary waves in open pipes, we need to derive how the frequencies of harmonics produced in that open pipe. So let us see formation of stationary waves in open pipe. Open pipe is an organ pipe. That open pipe, both ends of the tube are opened. Then it is known as open pipe and it is an organ pipe. So we are taking open means both sides it will be open. So whenever sound wave is sent through a pipe from open end, it gets reflected from the other open due to the pressure difference, due to variation in pressure of the air molecules, it gets reflected. So antinodes are formed at the two open ends and node is between them. So you can observe at the diagram. So this we have taken the minimum frequency, which is also called as fundamental or first harmonic. So here, when sound passes through this open pipe, at this due to pressure variation, here atmospheric pressure present, inside the tube pressure will be low. So due to that pressure variation, here the waves will reflected from one end to other end. So in between we can see node is formed. At the open ends, antinode is formed. And if we take higher than the fundamental frequency, the air column present in the open pipe is observed this way. One complete segment and two half segments. And condition at open end, antinode is formed. In between, where displacement or amplitude is minimum, nodes are formed. That is for second harmonic. So here, antinode to node length of air column is lambda by 4. Even here also, in the fundamental frequency, lambda by 4. So length of air column in the first harmonic, you can take it as lambda by 2. Next column, lambda by 4, lambda by 2, lambda by 4. It is lambda by 4, lambda by 2, lambda by 4. Length of the eighth column for the second harmonic, means that possible frequency is the second harmonic. The length of eighth column here we can take it as lambda by 2 plus lambda by 2, which will be equal to 2 lambda by 2, which gives you lambda. And we observe one more. So here lambda by 4, lambda by 2, lambda by 2, lambda by 4. Because node to node, or you can take antinode to antinode that way. Here the total length at the third harmonic, it will become 3 lambda by 2. So length of 8 columns through the open argon pipe, we observe for the fundamental or the first harmonic frequency, for second harmonic, and for the third harmonic. Now let us go to find the frequency with the first harmonic. Formula is same as like stationary waves. So let us find frequencies of harmonics in open pipes. First harmonic or fundamental frequency. In first mode of vibration, 2 antinodes and 1 node is formed. So length is being equal to lambda by 2. As it is first harmonic, we kept 1. So lambda 1 is equal to 2L. So fundamental frequency, take it as mu1, which is the first harmonic. We can write first harmonic. So frequency formula is V by lambda. So we need to write for the first harmonic mu1, mu or f, both are frequency representations. So mu1 is equal to V by lambda 1. So where lambda 1 is 2L. So you can substitute V by 2L. Next, similarly for the second frequency, we calculated their length of the 8 column 2 lambda by 2. As it is second harmonic, we are representing like lambda 2, which can also write it as lambda 2. Then substitute in the frequency formula for the second harmonic, mu2 will be equal to, means that corresponding frequency mu2 will be equal to V by lambda 2. Lambda 2 is being equal to L. It can also written as 2V by 2L. So V by 2L is first harmonic. So here in open pipe, the second harmonic is being equal to 2 times of the first harmonic. So 2 mu1. Next, let us go to third harmonic. Similarly, here also length of the A column. At the diagram we given length of A column through that open pipe for the third harmonic, where 4 antinodes and 3 nodes are formed. So we can see here L is equal to 3 lambda by 2. So from this we can write lambda, which is for third harmonic, it will be equal to 2L by 3. Then substitute in the frequency formula. Frequency formula is mu is equal to V by lambda. Lambda is 2L by 3. Then it becomes 3V by 2L, which is equal to 3 times of the first harmonic. So the harmonics can be derived in the same way for further frequencies, for higher frequencies. So the harmonics will be in the ratio through open pipe is 1:2:3. So the frequencies of the stationary waves in a open pipe is 1:2:3. Next. Next, here we are given with third about the stationary waves, like a third concept, how the stationary waves form in closed pipe. You can observe the diagrams here. We are given with the closed pipe, and there is a vibration of 8 column in that closed pipe as per the frequency of that sound note. With a minimum frequency, we can observe the 8 column. higher than the minimum frequency, next air column, and more higher than the minimum frequency, which is fundamental frequency. So go on, the vibration of air column is increasing by increasing the frequency. So we can see formation of stationary waves in a closed pipe. In this, the condition at open end, antinode is formed, and at closed end, node is formed. Explanation: when a sound wave is sent through closed organ pipe, the wave gets reflected at the end of the pipe. So you can see it gets reflected at the end of the pipe. These incident and reflected waves having the same frequency, traveling in the opposite directions, are superimposed, means combined, along the length of the pipe and form longitudinal stationary wave. So at the open end always an antinode, and at the closed end always node is formed. So let us see the frequency of stationary waves in a closed pipe. So first, for the frequency, we go with first harmonic. You can see in the first diagram, that is the fundamental or first harmonic frequency. The length of the air column is antinode to antinode, means lambda by 4. So length is lambda by 4. From that, lambda is equal to 4L. So frequency, see, here they represented frequency with N. So we can represent N or F or mu. But throughout the question maintain the same representation for that quantity. So for the first harmonic, which is the minimum frequency, equal to V by lambda, where V is equal to same, means here we can say longitudinal stationary waves. You can find the velocity of longitudinal waves. So here we are not substituting V value, let it be V only. N1 equal to V by 4L. This is known as fundamental frequency. Next possible, because you can observe here, length of the air column, here to here lambda by 4, here to here lambda by 2. So length of air column for the higher frequency, higher than fundamental frequency, it is being equal to lambda by 4 plus lambda by 2. So you can take like 3 lambda by 4. Taking LCM, it will be 3 lambda by 4. So lambda by 4 is the length of fundamental frequency, air column with fundamental frequency. 3 means 3 times of fundamental. So it is called third harmonic. And here you can observe in the third diagram, lambda by 4, node to node lambda by 2, again node to node lambda by 2. It is equal to, length will be equal to 5 lambda by 4. Means 5 times of the fundamental frequency length. So it is fifth harmonic. So we have observed length of air columns with higher than the fundamental frequencies. So after the fundamental frequency, it is observed that third harmonic are first overtone, because length of air column is being equal to 3 times of the length of air column of fundamental frequency. So next possible harmonic should have one more node and antinode than fundamental frequency. So the vibrating length is being equal to 3 lambda by 4, lambda equal to 4L by 3. So the corresponding frequency is called third harmonic. Formula is V by lambda. V by lambda is 4L by 3, so it becomes 3V by 4L, which can be written as 3 times of fundamental frequency. It is also called as third harmonic or first overtone, because higher than the fundamental frequencies are overtones. Next, it is observed in the diagram length of the 8th column higher than the third harmonic is 5 times of length of 8th column of fundamental frequency. So it is given that L equal to 5 lambda by 4, then lambda equal to 4L by 5. Substitute in the frequency, the corresponding frequency, which is the 5th harmonic, will be equal to 5V by 4L. By substituting lambda, it becomes 5V by 4L, 5 times of fundamental frequency. So it is known as 5th harmonic or second overtone. So the ratio of harmonics in closed pipe are in the ratio of odd numbers, like 1:3:5, so on. So this way you can calculate the higher frequencies of stationary waves in closed pipe. So remember, in open pipe, frequency ratios are 1:2:3. In closed pipe, the harmonics or frequency of stationary waves are in the ratio 1:3:5. Here odd multiples. And next important in the waves, the concept of beats. What are beats? Obtain an expression for the beat frequency, where and how beats made use of. So we need to write the uses of beats also. You can see here, beats are produced due to interference of sound waves. Interference is nothing but principle of superposition. Same as like the stationary waves only, but here the sound waves, the only difference is two sound waves of nearly equal frequency. Means there is slight difference. In the stationary waves have the same frequency. Here there is slight difference. Are superposed, they will create a waxing and waning intensity of the sound. Means here maximum, waning means minimum. So we can observe the maximum and minimum loudness of the sound note in the formation of beats. This effect is called beats. We can see here, first wave and the second wave, which are having slightly different frequencies. Here frequency N1, N2. They combine to form the formation of beats. Third diagram, you can observe the formation of beats. So two such waves which are having slightly different frequencies superpose the new set of waves are called beats. You can observe here maxima, minima. So means intensity variation I can show with the separate diagram. Maximum, minimum. Again maximum, minimum, maximum, minimum. So intensity varies periodically. Here maximum, here minimum. So loudness also varies periodically in the formation of beats. So let us go to mathematical analysis. So how do we can calculate the beat frequency? Means difference in the frequency of the superposition of waves. Here I given N1, or you can represent like mu1, N2 or mu2. So difference in the frequency of the sound waves gives beat frequency. Let us see. We consider two waves y1 and y2 of nearly equal frequencies n1 and n2, each of amplitude A, amplitude same only. Superpose each other, then the resultant wave is given by. So here we are taking A sine displacement equation in this form, A sine omega t. For first wave A sine omega 1t, for second wave A sine omega 2t. Superposition means combination. So we are adding. Taking omega 1 in terms of frequency and omega 2 also. Whereas omega we write in terms of frequency 2 pi mu. So for first wave 2 pi mu 1, for second wave 2 pi mu 2. Now it is sin A plus sin B form. Sin A plus sin B, which is equal to 2 sin A plus B by 2 cos A minus B by 2. Whereas A common, so they written 2A sin A plus B by 2 term here, cos term here, cos term first. So we have written 2 pi also they took common, 2A cos 2 pi of mu 1 minus mu 2 by 2 into t, sin 2 pi of mu 1 plus mu 2 by 2 into t. This is sin A plus B by 2 term, cos A minus B by 2 term. Now y is equal to A sin 2 pi mu 1 plus mu 2 by 2 into t, where means instead of 2A cos 2 pi of mu 1 minus mu 2 by t, they have written it as A. Now this equation represents amplitude. AR means resultant amplitude of beats. How we have given resultant amplitude of stationary waves. Here also same. After the superposition, beats are formed. So this is the amplitude of beats. So the frequency of resultant wave is mu 1 plus mu 2 by 2. And the frequency of the amplitude is mu 1 minus mu 2 by 2. Because frequency of beats can be calculated by taking difference in their frequencies. Average sound note can be heard, so that is what here resultant wave is mu 1 plus mu 2 by 2. And by using this amplitude, we can find intensity of the sound will be maximum when amplitude is maximum. So when 2A cos 2 pi of mu 1 minus mu 2 by 2 into t is maximum, sound will be maximum. So we give, see here, we give the condition. For what values it will be maximum? 2 pi into mu 1 minus mu 2 by t into 2 into t is equal to k pi. So for pi values, usually cos will be maximum. So where k is an integer, 0, 1, 2, 3, so on. So we can write time period of the beats. So from this we can write t is equal to, both sides pi cancel. Then t is equal to k into, even 2 also cancel. K into 1 by mu 1 minus mu 2. This is the time period formula. Put k value 0 and next k value 1 means 1 by mu 1 minus mu 2. So when it is 0, 0, next 1 by mu 1 minus mu 2, next 2 by mu 1 minus mu 2, 3 by mu 1 minus mu 2, so on. So at these time, at these value, at this duration, we can hear the maximum sound. So what are the intervals? 0 comma 1 by mu1 minus mu2 comma 2 by mu1 minus mu2, so on. Now if we take time interval between any two successive maxima, means between these two, 2 minus 1 gives 1 by mu1 minus mu2. 3 minus 2 gives 1 by mu1 minus mu2. So time interval between any two maxima, we are getting 1 by mu1 minus mu2. And from this is time period, frequency will be equal to 1 by t. So which will be equal to mu1 minus mu2. That is the number of maximum per second is equal to mu1 minus mu2. So first we measured at what intervals sound is maximum, and by taking difference between any maxima, we are getting 1 by mu1 minus mu2. And from that frequency of the beats, B we are writing here is the beat frequency, or frequency of beats will be equal to mu1 minus mu2. This is the equation. Next point, intensity of sound will be minimum when amplitude is minimum. Means cos 2 pi of mu1 minus mu2 by t into t is minimum. Means 0. If that value is 0, we get minimum sound. So if we take time interval between any two minima, we get 1 by mu1 minus mu2 only. Here you need not to express again the condition, like you have to take here like 2 pi into mu1 minus mu2 by 2 into t is equal to like 2k minus 1 into pi by 2. So for these values, it will be minimum. So both sides pi cancel, 2 cancel, t is equal to 2k minus 1 into 1 by 2 into mu1 minus mu2. Putting k is equal to 0, 1, 2, 3, so on. We get the time intervals for the minimum sound. And if you take time interval between any two minima, we get the same as time interval between two maxima. That is 1 by mu1 minus mu2. So here also number of oscillations per second is called beat frequency. We are getting approximately mu1 minus mu2, which is beat frequency. So difference in the frequency of sound notes are called beat frequency. Next, they are asking importance of beats. So here we can see beats can be used in tuning musical instruments. These are used in detecting dangerous gases in mines, and these are used to produce special effects in cinematography. Can be used to determine the unknown frequency of the tuning fork. And beats are used in heterodyne receivers range. So these are the uses of beats where we can use. And students, there are a few important problems about stationary waves in organ pipes. Here we are given with one question. A closed organ pipe 70 centimeter long is sounded if the velocity of sound is 331 meter per second. What is the fundamental frequency of vibration of the air column? It is a closed pipe. It is closed organ pipe. So fundamental frequency in the closed organ pipe is means minimum frequency, the first frequency. It is calculated as V by 4L. This we have to find. So they substituted V value 331, 4 into L value, length of air column is 70 centimeter is given. So we need to convert that into meters. So 70 into 10 power minus 2 meters, which is equal to 0.7 meters. So then it is given as 118.2 hertz. Next question. A vertical tube is made to stand in water so that the water level can be adjusted. Sound waves of frequency 320 Hz are sent into the top of the tube. If standing waves are produced at two successive water levels of 20 centimeter and 73 centimeter, what is the speed of the sound waves in the air in the tube? Actually, it is the question about resonance tube. Resonance tube is nothing but closed organ pipe. So they're given the two successive water levels of that tube. Consider them as resonating lengths. So resonating length in the first tube 20 centimeter. Resonating length L2 is given as 73 centimeter. So resonance tube experiment is to calculate the speed of the sound wave. So the formula is V equal to 2n into L2 minus L1. 2 into frequency of the sound wave is given, that is 320. So in that medium, so that sound waves are through the water. So we are finding velocity of that sound through that water. Medium is water here. So by using this equation, V equal to 2n into L2 minus L1. So V equal to 2 into 320 is 640, 73 minus 20 is 53, which is equal to 33,920 centimeter per second, which is equal to 339 meter per second. So you have to remember this. Whenever they given resonant length from the resonance tube experiment, how to calculate the velocity of the sound in a particular medium, that is 2n into L2 minus L1. So students, this is the required discussion today. All important long answers from the waves and few model numericals. Thank you.